We're going through some pretty challenging times right now, and you may or may not feel up to the task. If you don't, you wouldn't be the first one. When the Lord came to Moses at the burning bush and told him to go to Egypt and lead the people out, Moses had some pretty big reasons why he wasn't the person for the job. And the Lord didn't really disagree with that. He just said, well, it's going to be me doing it rather than you. So if you don't feel up for the job, and I don't always either, realize that the Lord doesn't call the qualified, he qualifies the called. He's not calling me because I'm able to do the job. He's calling me because I'm willing to do the job. There's a big difference. This lesson is over section 11.1, the second part. So we already had an earlier lesson on this, and now there is a note packet, section 11.1, part 2, and a spreadsheet 11.1 simulation examples, part 2, posted on Brightspace. It is the second lesson on the same topic of Monte Carlo simulation, so I won't go through the background again. What I want to do for this lesson is just 2 examples, and one of them is a piggyback on the one we've done before. So, refresher, this company is producing car batteries. We know their average lifetime and standard deviation and the fact that they're normally distributed. The company puts on a warranty and expects to pay refunds to a few customers whose batteries fail before the warranty period is up. The company expects to sell 1,000 batteries, and in the last lesson, we were calculating things like, well, what's the average payment per battery sold that the company would expect to make, and what proportion or probability of the batteries will require a refund of more than $6. And a lack of precision in the results from last time were that the numbers were bouncing around. Every time we did a recalculation of the spreadsheet, the random numbers changed, and our guess for the average refund and for the proportion requiring more than $6 refund changed. But this is exactly the kind of thing that inferential statistics is designed to handle. So the new part here is let's combine our ideas of confidence intervals from chapter 6 with Monte Carlo simulation that we just introduced last time. So let's go to the spreadsheet, and first let me show you what's in the tabs here. There are 3 of them. In sheet 3 are some of the background information for the battery example. I'll work on this sheet some. In the battery tab is everything that we're going to do, so that's the completed worksheet. And then airline is a separate example that we'll do next. So let's tackle those 2 questions that were posed on the note packet. Confidence intervals for the mean and for the proportion greater than $6. Here basically is the spreadsheet as we left it last time. I rearranged things to be a little cleaner, but in the upper left-hand corner are the numbers given in the problem. Here is a random number generator that gives normally distributed random variables with the right mean and standard deviation. Here is a cell that calculates what the payment is going to be. So if the battery fails before warranty, it calculates a payment. If the battery doesn't fail till after warranty, the payment is 0. Then here was a data table of 1,000 simulations of this and how much the payment was going to be for each of the batteries. Up here is the average of those 1,000 simulations. And here was a count of how many of the trials resulted in a payment of more than $6 divided by the total number of trials. So this is a probability or proportion. And then remember, as we refreshed, these numbers bounced around a bit, and that's kind of what the current topic is designed to account for or to overcome. Okay, if I'm going to do confidence intervals, reminder that this is back on page 67 of the notes in section 6.4. I was going through calculating T alpha over 2 number and a margin of error, and then adding and subtracting the margin of error to the point estimate, and so on. So that's what's happening here. We'll implement it in the spreadsheet this time. I will need the standard deviation, and it is going to be calculated as, let's see, standard deviation of a sample, and it is of these same 1,000 items. We are given a confidence, so I'll just put that in the spreadsheet of 95% or 0.95 as a decimal. And then this number alpha was 1 minus the confidence. Then remember that we were using this Excel command t.inverse.2t. So t distribution, inverse means find a t-score, and it's a two-tailed. The alpha is given regarding the area in two tails. So let's calculate that. It is t dot inverse dot two tail. And the two things that it needs are the alpha value and the sample size minus 1. So here was my 1,000. I put it in the spreadsheet so I don't have to type numbers into my formula. Minus 1, and that gives us a number 1.96 that I now can use to calculate the margin of error. And the margin of error is coming from our formula T alpha over 2, and then times S, the standard deviation, divided by square root of n. So here is the T number times the S number divided by the square root of the n number. Okay, once we have that, once we have the margin of error, the way that you calculate the margin of the confidence interval is to go up and down from the average by the margin of error. So let's say confidence lower boundary, confidence upper boundary. And those are calculated by taking the average and subtracting the margin of error, and taking the average and adding the margin of error. Okay, here is now a confidence interval. If I recalculate the spreadsheet, everything changes, including the confidence interval. But now this is not the right way to think about it. You only should do this once. I'm just showing that it does depend on the simulation values, but you only do this once, and you record the result as a confidence interval, and that captures the idea that we know there's variation. That's why we're giving an interval instead of just a single number. So we can say something like, we are 95% confident the average refund will be between, and now I just give the two numbers in my confidence interval, about 0.71 and 1.06. These are units of dollars, so between 71 cents and $1.06. And done. Somebody reading this and trying to use it to make a decision would say, okay, we can't get the exact value, but it's more than likely between these two numbers, and make your decision accordingly. Now, regarding the proportion of batteries that are going to require at least a $6 warranty payment, let's keep this in parallel with the one calculation that we did for the mean. There is no standard deviation for a proportion, but there is a confidence. And this time it was given in the problem to be 90%. So alpha is again 1 minus the confidence. And now for proportion problems, we actually used a z distribution. Not a big difference, but I'll go ahead and do that here. So the z value came from a command called normal distribution .s.inverse. So normal distribution, standard normal, and then calculate a z-score rather than a probability. And here, this command works a little differently. It wants the value 1 minus alpha over 2. You can look back in the notes and see that that's what needs to be entered here. Then, margin of error. And this problem is for a proportion. So if I look back on page 69, and I can see how to calculate the margin of error for a proportion. So z alpha over 2, that number, and then times the square root of the p times 1 minus p expression. So here we go, equals z times square root of a fraction whose numerator is the proportion times 1 minus the proportion. This is p times 1 minus p divided by the sample size 1,000. All right, and then the margin of error can be calculated similarly. I need the confidence interval, I should say. I need an upper and lower bound on the confidence interval, and I get those by taking the proportion and subtracting the margin of error, and taking the proportion and adding the margin of error. So here are the boundaries of my confidence interval. Again, no need to do a lot of simulations. That's already been done. The numbers are 0.051 and 0.077 basically. So I can say something like, we are 90% confident the proportion of all batteries requiring a refund of more than $6 will be between And now I forget my own numbers, 0.51 and 0.051 and 0.077. So 6 or 6.5 somewhere is kind of in the middle here, and that's the boundary, the ballpark of where this proportion is going to be. Roughly 6 to 7% of the batteries are going to require a refund of more than $6. Okay, that finishes that example. Again, the completed spreadsheet is here in the battery tab. And now let's go to the second example. At the top is an Excel command that we'll need to use a little later, but let me give the background for the example. Here, an airline is selling tickets. So obviously an airplane has a fixed number of seats, in this case 50. And so whatever else happens, no more than 50 passengers can fly on this flight. Suppose the airline can make a profit of $100 per ticket sold. So obviously it wants to sell as many tickets as it can. And you might think, well, just sell 50, but past data has shown that not everybody who buys a ticket shows up. And so airlines routinely overbook. They sell more tickets than they have seats available. And if more people show up to actually fly on the day at the airport, then the airline offers vouchers to people who aren't able to fly and have to take a later plane. So depending on the situation, and those vouchers can be worth more or less money. In this case, we're saying that this airline is going to offer $300 vouchers to passengers who are denied a seat on the airplane. We'll use a binomial distribution to model the number of ticket holders who show up. So 52 people, say, purchase a ticket, but that doesn't mean that 52 people will show up, and we'll use random number generation to model how many actually do show up. And finally, the airline has a finite number of customers. I mean, it can't just sell as many tickets as it wants. It has to think about demand, customer demand. So based on past data, the airline believes that the number of customers who will actually try to purchase a ticket, if available, can be modeled by a random variable with this discrete distribution. So from past data, it's saying that, well, we're pretty sure that between 48 and 54 customers are going to try and buy a ticket on this flight. And here are the corresponding probabilities for each of those numbers. The main job here of the airline is to decide how many tickets to sell, or to try to sell at least. What kind of cap to put on ticket sales. Obviously, it doesn't make any sense for the company to cap ticket sales below 50 tickets. The plane holds 50 people, so the airline will try to fill it up if they can. But it may not make sense for the airline to sell 60 tickets, for example, because then the flight will be overbooked most likely, and we'll have to start paying these $300 vouchers. So somewhere in the middle, maybe there's a happy medium where the airline will financially do the best. So let's generate a confidence interval for this again, and use it to decide what's going to happen if we cap ticket sales at 50 tickets, 52 tickets, or 54 tickets, and then make a recommendation to the management of this airline what decision should be made. So this is a fairly complicated spreadsheet, and I'm not going to fill it out. I'm going to refer and walk us through what's actually been completed. So here are formulas being shown. And let's start here in the upper left-hand corner. So here are the numbers that I know for the problem. The plane has 50 seats. It's going to make a profit of $100 per ticket sold. It's going to pay $300 per voucher that it has to pay for people who get bumped. Here is the average no-show rate, and here is the ticket cap that the airline is going to put on. This place in blue is what's going to be of interest here. We can change this number 50 to something bigger and see what that does to our profit. Let's move over, let's see, here. So over here is a place where I'm able to generate a discrete random variable. So recognize this setup, the number of customers and their corresponding probabilities is here. And then I've divided the interval 0 to 1 in little chunks, as we've done on previous examples. And I'm showing formulas right now. If I look at the actual numbers, you can see that things are working out. Okay, so the next thing I want to do is come here and do some calculations for a single customer and what impact that has on the flight as a whole. So here now, let's generate the number of people who are going to attempt to buy a ticket. That's what this table over here is for. So I use my VLOOKUP command to go in here and grab one of these numbers from 48 to 54 with a random number generator. Here is the number of tickets sold. Well, there are two things that go into that. One is if I put a ticket cap, then by definition, I'm never going to sell more than that. But I also can't sell any more tickets than I have customers. So this MIN or minimum command says, take the smaller of the ticket cap and the number of customers trying to buy a ticket. And that minimum will be the number of tickets that are actually sold. The next line is generating a random guess for how many passengers actually arrive at the gate to board the flight. So at the top of the note page was the suggested usage of a command binom inverse. And what it wants is the value n, which is the number of tickets that were sold. So this is the potential number of people that could come to the airport. And then the next thing it wants is what's the probability of each individual passenger actually coming. So if the no-show rate is 0.04, if I take 1 minus that and get 0.96, that's the probability of each individual passenger showing up. And so this then generates, this formula generates the number of passengers who show up in my random simulation. Then I have to decide how many people are going to get bumped. So the way I'm doing that is, first of all, checking whether the number of passengers who arrived is greater than the number of seats on the plane. If so, then somebody has to get bumped, and how many people get bumped are the number of passengers arriving minus how many seats are available. On the other hand, if fewer passengers than seats have arrived and are attempting to board, then nobody's going to get bumped. So I can choose a 0 in that case. Now that I know how many passengers are going to fly and how many got bumped, I can calculate the finances here. The profit from sales is going to be how many tickets were sold times the profit per ticket. And the rebooking cost is going to be how many passengers were bumped times the voucher payment that I have to give to each one of them. And finally, the net profit then is going to be my sales profit minus my rebooking cost. And when I do some recalculation, you see numbers changing here. So far, nobody has gotten bumped. Maybe we'll get a case where somebody does, not that it matters. Oh, I see why, because the ticket cap is at 50. Nobody is going to get bumped with that scenario. Okay, so the next thing I want to do is simulate this a lot of times. So in columns A and B, I have a lot of data in a data table. And each of these is holding a value of the net profit for that simulation. Okay, now let's move over here and start calculating answers to the questions that were asked. I'm going to show formulas again. So first of all, I want a note that we want a confidence interval for the airline's net profit. So let's calculate the average profit over all of these simulations, the standard deviation of that same range of data, because this is going to be a question about means. Here's the confidence, and now I'm in a similar way to the previous problem, calculating a t-score here and a margin of error that goes with it, and then taking my average minus and plus the margin of error. So here you can see the numbers. If I do some recalculation, you see the numbers jumping around, but not by very much. And at any rate, I have my answer to the first question. The confidence interval is 49.84 to 49.90, basically. So I'm just going to write the numbers. 49.90. And the verbiage that would go with that is something like, we are 95% confident the profit will be between $4,984 and $4,990 if we cap ticket sales at 50. Then the problem asks us, well, what if we sold 52 or attempted to sell 52 tickets, up to 52 tickets? So I will change that number to 52 and do a few recalculate. Okay, here's a situation where somebody did get bumped. I sold my 52 tickets, and by luck of the draw, all 52 people had to happen to show up at the airport. I only had 50 seats, so 2 people got bumped. I had to rebook them and pay this much. The rest of the calculations still carry through, and I get a confidence interval of 5,013 to 5,033. And finally, if we try to sell more tickets and don't cap sales until we get to 54 tickets here, and I get a confidence interval of 49.85 to 5012. 49.85 to 5012. Second part of the question says, okay, so to maximize profit, at what level then should we cap ticket sales? Well, I'm looking at these confidence intervals, and I notice that 52 tickets is clearly better. In fact, if I were to graph these things, here's an interval for 49.84 to 49.90. Here's an interval for 5013 to 5033. And here's an interval for 49.85 to 5012. So the three intervals sort of stack up with each other this way. And we're 95% confident that the mean is somewhere here, here, here in each of the three cases. So the fact that this interval is considerably large, spans a considerably a range of considerably higher numbers than the other two, tells us that the 52 ticket sales is the best option. So best to cap sales at 52 tickets. This apparently is more likely to achieve the right balance between maximizing our ticket sales with minimizing our rebooking voucher payments. And we'll stop there.